The stuff of life is all over Earth, and we know that it's also on many of the asteroids in the asteroid belt. We can even find a geological history of the stuff of life on the planet Mars, where we know that a couple billion years ago, immense amounts of water once flowed. But, due to the constraints of current technology, our ability to measure for the stuff of life beyond our star system is limited. It's not like we can just send a space probe off to some nebula 15,000 light years away. Real life, and the real cosmos, isn't a Star Trek episode. A journey of such literally cosmic proportions would require countless millennia. After all, even at this point in 2024, the farthest any man-made spacecraft has ever gotten so far is only an infinitesimally small amount beyond our star system, and those would be the unmanned Voyager 1 and 2 probes, launched almost 50 years ago. Fortunately, the technology available to modern astronomy has grown immensely, and our ability to put some telescopes in orbit has also helped a great deal. The pinnacle of that technology presently is the James Webb Space Telescope, or JWST. And one of the projects it has been engaged in is trying to understand just how common the stuff of life may be beyond our star system. In other words, is there a realistic chance that some or even many star systems with the stuff of life exist beyond our world? Having a sense of these answers would not only inform us of the usefulness of looking for life beyond our Earth, but also help us to understand the history of our own star system. There is a program going on right now that is invested in discovering the answers to these very questions. It is known as JOICE Plus, or JWST Observations of Young Protostars. A relatively recent paper published on 30th October 2023 in the Journal of Astronomy and Astrophysics covered some of their findings so far. The paper was titled JWST Observations of Young Protostars, JOICE Plus, Detecting Icy Complex Organic Molecules and Ions. The paper discusses the program's search for COMS, or complex organic molecules. Now, these are ubiquitously detected in space in their gas phase, even though they are thought to be mostly formed on icy grains in space. But, till now, none have been discovered larger than the CH3OH molecule. Technological limitations made it very hard to look for them, but the JWST, with its ability to peer deep into the infrared spectrum, changes things. It can almost be said that the JWST can see through the dust in space due to its very high sensitivity and its spectral resolution in the critical 5 to 10 micrometer range, which is the fingerprint, according to the paper, of the region of oxygen-bearing COMS. The JOICE Plus program has a vast mission. According to the paper, in the JWST Observations of Young Protostars Plus program, more than 30 protostars are undergoing observation with the medium resolution spectrograph, the MRS, of the mid-IR instrument known as the MIRI. The goal of this study is to comprehensively explore the COMS, or complex organic molecule, ice signatures in one low and one high mass protostar. Those stars are NGC 1333 IRAS 2A and IRAS 23385 plus 6053 respectively. This image was shot by MIRI, the mid-infrared instrument on the James Webb Telescope, and it shows the region of space near IRAS 23385. It is the product of a single exposure at a wavelength of 15 microns, which have been assigned an orange color. And the Webb study focuses on it and a nearby star, IRAS 2A, which they are particularly interested in because it is a low-mass protostar. This means this star is very similar to our own Sun, and so observations made of the development of the system around this star may tell us some things about how our own star system formed. It is well known that CHONS elements exist in cold nebulas such as this. CHONS stands for carbon, hydrogen, oxygen, nitrogen, and sulfur. These are elements that form common and essential building blocks of life. And what the team is trying to discover is how these elements may recombine by way of chemical reactions in space, in what way and in what form, and whether these chemical combinations happen when the elements are in gaseous or icy states, and then ultimately how the chemicals are transported to the planets forming around these protostars. The outcomes of this dark chemistry that happens in these cold nebulae form the complex organic molecules the researchers are interested in. According to the JOIS Plus leader, Wil Roca of the Leiden University in the Netherlands, the detection of CHONS in ices suggests that the solid-phase chemical reactions on the surfaces of cold dust grains can build complex kinds of molecules. It is presently believed that the complex molecular reactions required to make CHONS happen during the sublimation of these ices as they float about within the nebula. The team has so far found quite an array of complex organic molecules, including acetic acid, formic acid, and ethanol or alcohol. If the reactions that form these chemicals can happen when the chemicals are cold, and in fact when the chemicals are icy or sublimating, that helps us to understand how the chemicals could then move from the nebulous environment to the surface of planets. The CHONS, in the form of ice, may become part of asteroids and comets that are eventually drawn into protoplanetary disks and collapse into a new planet, becoming ultimately part of its structure and makeup. The cold nebulae, where these elements and the complex organic molecules can be found, have always been regions of scientific curiosity. But it wasn't until the James Webb Telescope went into operation that a device came into existence with the sensitivity to detect these things. And the study of the evolution of chemicals buried deep within the cold regions of nebulae have been going on for quite some time. In a preceding article entitled Webb Unveils Dark Side of Prestellar Ice Chemistry, a team of scientists targeted ices found in a particularly cold and dense region of the Chameleon-1 molecular cloud, which is about 630 light-years from Earth. There, they found carbonyl sulfide, ammonia, and methane, along with one of the simplest complex organic molecules, methanol. Point of note, the researchers consider molecules to be complex when they have 6 or more atoms. These findings provide insights into the dark chemistry stage of the formation of ices on the interstellar dust grains within the nebula. Those ices, which will eventually grow into centimeter-sized pebbles that will ultimately come together by way of the swirling vortices of protoplanetary disks to form planets. And this research proved for the first time that complex molecules, including organic complex molecules, can form in the cold icy depths of molecular clouds long before stars are born, as if these nebula were already preceded with the stuff of life. And this life stuff will be inherited by the planets that form within those nebulae in an already advanced form. The research not only indicates the presence of the stuff of life, but researchers were able to detect the sulfur-bearing ice, carbonyl sulfide, allowing them to estimate the amount that was embedded in icy prestellar dust grains. This is the first time such a thing has been possible, and that it is possible at all is thanks to the JWST. These measurements allowed for the determination that there was more of this life stuff, such as sulfur, within the nebula than had been previously observed. And there are likely more CHONS elements, or carbon, hydrogen, oxygen, nitrogen, and sulfur, hiding within the nebula as well. One of the tasks before the research team at this time is to figure out just where and how these elements are hiding. Perhaps they are to be found in the form of ices, or soot-like materials, or perhaps in and among rocks. The abundance of CHONS materials within the nebula indicate that there could be a great deal of diversity within the chemical makeup of the planets that form from this nebula. Yet, I think one of the most interesting things about these observations were how they were made. Certain frequencies of starlight passing through the cloud are absorbed by the chemicals within the nebula. The absorption leaves behind chemical fingerprints, absorption lines, which are then compared with laboratory data to determine what elements are found within the data. And so it can truly be said that it was starlight that revealed the presence of alcohol, vinegar, and ant sting poison out in deep space.